Welcome back to the deep dive. This time, we're going deep into distributed databases.
Oh, fun.
Yeah. We've got a whole pile of videos and articles to go through.
Nice.
All about a tricky problem.
Yeah.
Time. Yeah. How do these systems spread across so many servers? How do they all agree on what happened when?
It is a question we don't really think about that much, do we? I mean, in our everyday lives, we just kind of take for granted that time is a constant, right?
Right.
But as soon as you go into the digital realm, when systems are scattered all over the place, it gets a lot more complicated. It's almost like the internet has its own theory of relativity.
Yeah. It's like that presentation by John Daly that you sent over.
Oh, yeah.
He made the point that just figuring out what came first can become a real headache when you've got multiple computers in the mix.
Yeah. Just imagine like those tiny little differences in clocks across different machines.
Right.
Network hiccups that delay messages, even by a fraction of a second. Suddenly, something as basic as time becomes this slippery concept.
And it's not just a theoretical problem.
Yeah.
It has real-world consequences. You remember that example from Dan Rubinstein's talk about the text message game?
Oh, yeah.
Where Ben and Sarah are both trying to win by, texting each other about a new game.
Right, yeah.
And because there's no central authority to timestamp those messages, it becomes impossible to know who actually sent the message first.
Yeah, that seemingly simple game, it just perfectly captures that whole problem of causality in distributed systems.
Right.
When you try to scale that up to, a massive system with thousands or even millions of transactions happening every second, all across numerous servers.
Oh, yeah.
Knowing the order of events becomes absolutely critical for keeping your data consistent and avoiding all sorts of nasty problems.
So how did the people who first built these systems, how did they try to tackle this?
Well, early on, they came up with these things called Lamport clocks. It was a pretty good starting point, but it had some serious flaws. For one thing, you could run into these weird ties. If two events happen at basically the same time, how do you pick a winner? It was arbitrary and, well, things could get out of sync.
Uh-oh.
Even worse, these early systems, they just couldn't handle network partitions.
Network partitions. What are those like when the internet goes down?
Kind of, but on a smaller scale. Imagine two parts of your system suddenly can't talk to each other.
Oh, okay.
Imagine a wall suddenly appears between them.
Right.
That's a network partition. Early systems, relying on these Lamport clocks, they would really struggle to keep things in order when that happened. Actually, this whole problem has been around for quite a while. We're talking 1975, when that old RFC 677, the one,
Yeah.
it was trying to address this specifically for key value stores, kind of a sign of things to come.
Wow. So what happened next? Did someone come up with a better way to track time?
They did. Remember that locust paper we included? That paper introduced this idea of version vectors, a clever way to deal with those network partitions we were talking about. Instead of relying on a single timeline, version vectors track the state of each part of the system independently. It's like giving each server its own little clock, right?
Okay.
And then, you got to figure out how to combine those individual timelines into a coherent whole, which, trust me, is way harder than it sounds.
Oh, I bet. But the paper also mentioned something called CRDTs.
Yeah.
Conflict-free replicated data types.
Ah, yes, CRDTs.
What are those?
They're imagine data structures that are built to be super robust, no matter what those pesky network partitions throw at them. They're designed to handle these concurrent updates in a way that always gets you to the same consistent end result, even if those updates arrive out of order.
So, how does that work? Did you give me an example?
Okay, so picture a simple counter, right?
Yeah.
It can only increase in value. Even if two different parts of the system updated at the same time, like when they're disconnected, once they reconnect and merge their changes, that counter will still end up at the correct value. There's no need for a central authority to say, hey, this update came first.
Right.
It's because the updates themselves are designed to be combined without creating any conflicts. Pretty neat, huh?
So it's like the CRDTs are built to anticipate chaos and still come out on top.
Exactly. And that brings us to another cool innovation, hybrid logical clocks, or HLCs for short.
HLCs.
Yeah, they combine the best of both worlds. You've got those logical clocks, like the Lamport clocks we talked about,
Right.
Keep track of causality. But you also have physical clocks that give us a rough idea of, real-world time.
Right.
This helps us avoid some of those weird time warping issues that could happen with just Lamport clocks alone.
Okay, that makes sense. And this is what John Moore talked about in his presentation, right? About how important these HLCs were for his actual budget app to, like, keep everything consistent.
Yes, James Long, the guy who created it, he initially built actual budget as this, like, local first app using Spooklight. Worked great on his own computer, as a standalone Electron app. But when he tried to bring it to the web, he hit a wall.
Why is that?
Because SQLite, you see, it's designed for a single machine. It's not really made for the whole distributed cloud-based world of the web. SQLite relies on local storage, and it loves doing things synchronously. It wants everything to happen in a specific order.
Right.
But the web's all about asynchronous operations, where tasks can happen in parallel and kind of out of order. Trying to make SQLite work on the web is like trying to fit a square peg into a round hole.
So how did he solve it? Did he have to give up on SQLite altogether?
That's where things get really interesting. Instead of throwing in the towel, he created this project called Absurd SQL.
Absurd SQL.
An ingenious way to use IndexedDB, which is the web's built-in database, as a stand-in for SQLite.
Remind me, what is that again?
It's essentially okay for web browsers to store data locally, but it's designed to work asynchronously.
Right, which SQLite doesn't like.
Right. Doesn't like it at all. But he found a way to make them work together.
How?
So he created this mapping between SQLite's block storage system and IndexedDB. So SQLite kind of thought it was working in its usual setup.
Oh, clever.
Yeah, and then to mimic that synchronous behavior that SQLite loves so much, he used this really clever trick with atomics, a feature that basically forces operations to happen in a specific order.
So he created this tiny little perfectly ordered bubble within the web browser for SQLite to live in, like its own little synchronized world.
Exactly. And it really highlights how important data locality can be. Remember Max Neuenhofer's talk about those lock-structured merge trees, those LSM trees?
Vaguely.
They're all about optimizing data access patterns, making things run faster.
So remind me how they work.
So LSM trees prioritize these sequential writes, which are much faster for most storage devices, and then they periodically kind of merge and compact the data to keep reads efficient.
Gotcha. So instead of just thinking about when things happened, we're now thinking about organizing data by where it lives to make things run smoothly.
You got it. And this whole focus on data locality, it's essential for any data store, really, whether it's on a single machine or a huge distributed system. It's all about performance optimization.
So it seems like we've gone from worrying about the order of events to, like, optimizing their location. But how does all this apply to actually choosing the right database for a particular project?
That's a great question, and one we'll tackle in the next part of our deep dive. We've laid the groundwork here, explored the challenges of time and consistency in distributed systems, and we've seen some of those innovative solutions people have come up with. Now it's time to delve into the specific strengths and weaknesses of different distributed databases, help you understand how to pick the right one for your needs. Stay tuned.
Picking the right database is kind of like assembling a toolkit for a specific job, right? You wouldn't use a hammer to screw in a light bulb. Each database has its strengths and weaknesses depending on what you need it to do.
Right. But with all these databases, boasting about their scalability and performance and consistency, it's tough to know what's really important.
Yeah, you're absolutely right. And that's where understanding those different consistency models becomes crucial.
Yeah.
Remember those session guarantees we talked about, like in Mohammed Wahidov's presentation about the new KV store?
Yeah.
You're guaranteed to see your own changes, and the data won't suddenly seem to jump back in time.
Oh, right. So even if things aren't perfectly synced across the entire system, every millisecond, my experience using the app will still make sense.
Yeah.
Exactly. It's all about providing a consistent and sensible experience within a user session, even if, under the hood, the data is still, like, eventually reaching consistency across the whole system. It's kind of like having your own little pocket of consistency in a larger world.
Okay, that makes sense. What about all these other consistency models I keep hearing about, though? You mentioned eventual consistency earlier, and I've heard terms like strong consistency, too.
Let's decode them. Think of eventual consistency as, like, the laid-back approach.
Okay.
Changes to the data will eventually reach all the servers.
Right.
But there's no guarantee of exactly when.
So if I post a funny cat video, it might take a few moments for everyone around the world to see it.
Exactly. No need to panic.
Right.
This works well for things like social media or those content delivery networks where a little delay won't cause any major issues. Now, on the other side of the spectrum, we have strong consistency. It's the no-nonsense approach. Every single read and write must be reflected immediately across every node.
Yeah, that sounds intense.
It is.
When would you need that level of strictness?
Think of things like financial transactions,
Okay, yeah.
healthcare systems, stuff like that, where even the smallest inconsistency could lead to major problems. You absolutely need to know that every part of the system is working with the most up-to-date information.
I can see why that would be critical for those types of applications.
Yeah.
But strong consistency, it sounds like that comes with a cost.
There's always a trade-off. With strong consistency, you often have to give up some availability.
Okay.
If a network partition happens, the system might just refuse to process any writes until all the nodes are back online and in sync again. This keeps the data safe, but it could also lead to downtime or delays.
So it's like choosing between speed and accuracy.
Yeah, that's a good way to put it. And there are, other models that fall somewhere in between those two extremes. For instance, there's causal consistency, which makes sure that events that are causally related, they're always seen in the correct order, even across different nodes.
It seems like picking the right consistency model is key for building a distributed system that's both reliable and performs well. Are there any other factors that developers should be thinking about?
Data modeling is another crucial aspect. You remember how Karthik Ranganathan talked about denormalized tables in his Yugabyte DB talk?
Vaguely.
It's like, instead of breaking everything down into these really neat and separate tables, sometimes you have to strategically combine things to make them faster to access.
So it's about trading off some of the strictness for a bit of speed.
Exactly. It's a trade-off between storage efficiency and read performance. And this brings us back to those LSM trees.
Yeah. The data organization strategy.
Right. They're all about making those sequential writes as efficient as possible.
Gotcha.
Which is ideal for systems handling tons of writes, like a lot of these distributed databases.
It's amazing how all these pieces connect. Consistency models, data modeling, storage engines, they all play such a vital role.
They do. It's all about striking the right balance for what you need. Now that we've gone over these basic building blocks, let's get back to some of those specific distributed databases. What are their strengths? What are they best suited for?
I'm all ears. Let's start with CockroachDB, the one named after, well,
Yes. CockroachDB is known for resilience and scalability, and it's a strong commitment to consistency.
So we're talking banks, e-commerce giants, anything that just can't afford to go down and needs their data to always be in sync.
Exactly. Now, Yugabyte DB, it's also aiming for that high availability and scalability, but it has a slightly different focus, multi-API support.
Oh, right. It can speak different database languages like SQL, Cassandra, and Redis, right?
Yes. This makes Yugabyte DB really versatile, especially for organizations with all sorts of different data needs. It means they can use a single platform for everything. Makes life a lot easier for developers.
It's like having that universal translator for databases.
Exactly. And that leads us to a very important point. The world of distributed databases, it's huge and it's constantly changing.
Yeah.
We've only scratched the surface here. There are so many other players out there, each with its own quirks and strengths.
So it's not as simple as CockroachDB versus Yugabyte DB.
Yeah.
There's a whole ecosystem of databases out there,
Absolutely.
all competing for a spot in the developer's toolkit. What are some of the other notable ones we should know about?
Well, there's Amazon Aurora, for example. Lives up in the cloud, boasts about its performance and scalability. It works really well with the whole AWS ecosystem, offers things like read replicas and global databases. It's a popular choice for those cloud-native apps.
What about Google Spanner? I feel like that one gets a lot of attention for like its global reach and how it maintains consistency across vast distances.
Spanner's interesting. It leverages Google's huge network and their super sophisticated clocks to, keep everything in sync across continents. The catch is it's tied very tightly to Google Cloud Platform, so it might not be the best fit if you need a solution that can span multiple clouds.
So it's like a really fancy cruise ship,
Yeah.
smooth sailing, very consistent, but only going to specific destinations.
That's a great analogy. And then there's Foundation DB, which is this open source database that's known for being really flexible and tolerant of faults.
Okay.
It has a super adaptable data model and excels at transaction processing, making it suitable for all sorts of different applications.
It's like we're witnessing this Cambrian explosion of database technology, each one adapting to its own little niche in the ever-expanding world of data.
That's a fantastic way to put it. There's so much innovation in this field, but the important takeaway is that there's no single best distributed database. The best one always depends on the specific needs of the project. You have to think about consistency guarantees, data models, scalability requirements, and the overall architecture of the system, among other things.
Right. It's all about choosing the right tool for the job.
Exactly. And speaking of choosing the right tool, remember, the world of distributed databases is never standing still. What was cutting edge yesterday might be obsolete tomorrow.
So we have to keep learning.
You got it. You have to stay informed about the latest trends and be ready to adapt. And that's exactly what we'll cover in the final part of our deep dive. We'll talk about the newest trends, discuss the challenges and opportunities they present, and leave you with some, hopefully, thought-provoking questions about the future of this amazing field.
Okay, so let's talk trends. What's coming up in the world of distributed databases? Are we talking like self-aware databases that can write their own code?
Haha, that would be something else, wouldn't it? But the reality might be even more interesting. One of the big trends we're seeing is this rise of serverless databases.
Serverless? What does that even mean? Do they just float in the cloud?
Not exactly. What it means is all those nitty-gritty details of managing servers, they kind of disappear. Developers can just build their applications without having to worry about things like provisioning servers or scaling or even maintenance.
So it's like having a personal chef for your data.
Oh, I like that.
You just tell them what you want and they handle all the messy stuff.
That's a perfect analogy. It gives you a ton of flexibility and scalability, which makes it a really attractive option for applications that have those unpredictable workloads or need to be able to grow super fast.
But doesn't that mean giving up some control over your data and like the infrastructure? I feel like there are security implications there.
That's a valid concern for sure. You need to choose a provider you trust, one with a good track record on security. But what you gain is agility. You can focus on building new things, on innovation, rather than getting bogged down in all that server management stuff.
So it's like choosing between driving your own car and taking an Uber.
Haha, yeah. Sometimes convenience wins out over control.
Right.
Yeah.
What else is on the horizon?
Another trend we're seeing is this growing interest in multi-model databases, which, we touched on a little bit when we were talking about Yugabyte DB.
Right. The Swiss Army knife of databases.
Exactly. These databases can handle multiple data models within a single system, so developers can just pick the best tool for the job.
Right. Relational data? No problem. Document store? Done. Graph data? Can do.
It simplifies data management, and it streamlines the development process. And here's another really exciting development: the integration of AI and ML into databases.
Wow. AI in databases. What does that look like?
Imagine databases that can automatically optimize your queries,
Yeah.
detect anomalies in your data, and even predict future data patterns.
So it's like having a built-in data scientist working behind the scenes to keep everything running smoothly.
That's the vision. AI and ML have huge potential to revolutionize how we interact with data, how we manage it. It can make our databases smarter and more insightful.
These trends sound pretty transformative, but I have to imagine there must be, potential challenges and downsides as well, right?
Oh, absolutely. With any new technology, there are always hurdles to overcome. With those serverless databases, for example, vendor lock-in and security are things you really have to consider carefully. Multi-model databases, while they're super flexible, they can create a much steeper learning curve for developers who need to learn a whole bunch of different query languages and data modeling approaches.
Right.
And the integration of AI and ML, well, that opens up some important ethical questions about data privacy and the possibility of bias.
It seems like we should always approach new technology with a healthy dose of skepticism.
Agreed. It's important to carefully weigh the potential benefits and risks before jumping on any new bandwagon.
So after our deep dive into the world of distributed databases, what are some of the key takeaways you would want our listeners to walk away with? What should developers and companies keep in mind when they're building these data-driven applications?
The most important thing to remember is that there is no one right answer, no single best solution. The best choice depends entirely on what your application needs, the data model you're using, what kind of consistency guarantees you need, how much you expect to scale, and the overall architecture of your system.
Right. Choose the right tool for the job.
Exactly. Second, this field is evolving so rapidly, brand new solutions pop up all the time, and the old ones are constantly getting new features and capabilities. It's a really exciting time to be in this space.
But we have to keep learning.
Yes, always be learning. And finally, remember that these distributed databases are really powerful tools. They can help you build applications that are resilient, scalable, and rich with insights. But unlocking that power requires, a deep understanding of what's going on under the hood, a careful evaluation of the choices available, and a willingness to keep up with the latest trends.
So we need to choose wisely, stay curious, and be ready to embrace the potential of these technologies to shape the future.
Well said.
This has been an amazing conversation. I feel like I've learned so much.
Me too.
As we wrap up, I have to ask, what do you think the future holds for distributed databases? Any predictions?
That's a great question. With, the rise of edge computing and all these internet-connected devices, I think we're going to see a push towards even more decentralized data architectures. How are these technologies going to evolve to handle a truly interconnected world? That's the question I think we'll all be trying to answer in the years to come.
It sounds like there are exciting times ahead. And with that thought-provoking question, we'll wrap up this deep dive. Thanks for joining us.
It's been a pleasure. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible.